So section 6.4 is called proportional reasoning, and we're going to look at taking what we have learned about ratios and using them as ways to compare quantities. So the ratio notation that we have been using for other purposes right now is actually written as the fraction a over b, or you can put it with a semicolon, or with a colon in between it, a colon b. We read this when we see it as a to b. So one of the ratios that you guys will hear often are is a ratio of like teacher-student ratio, or student-teacher ratio, depending on how they do that. And they always say something like 1 to 12, right? Or 12 to 1, depending on which order they're doing it in. So those are ratios. There's a couple different kinds of ratios. One ratio is called part to whole, and the other ratio is called part to part. So what happens when you're doing these different kinds of ratios is it's how things are being compared. So an example here talks about there are 15 students, 7 make A's on the test. The part to whole ratio compares 7, the number of A's on the test, to the entire class, the 15 grades. A part to part ratio would compare the 7 A's to the number of not A's. So that's a 7 to 8 ratio. So there's nothing about either of them that's sort of better than the other one, but they definitely mean something different. And so if you're thinking sort of the wrong one, you might come to a conclusion that doesn't quite make sense if you're not being a little bit careful. So what we're going to do on the first couple example is move between those two types of ratios. So on example number 1, we've got the ratio of boys to girls in the class, and it's 2 to 3. So what it means is that for every 2 boys, there are 3 girls. Does that make sense? And if you take a look at combining them together, that means that there's 5 kids total every time you do this sort of grouping up or partitioning off. So if we're wanting to compare the number of boys to the class in total, right, as a whole, we can take a look at these 3 numbers to make that comparison. So for every 2 boys, there's 3 girls. 2 and 3 make 5 for the total amount of kids. So when we're comparing the boys to the total, that's a 2 to 5 ratio. Or if you prefer, you can write it like that, of course, too. So that's going from a part-to-part comparison into a part-to-whole comparison. So this one, as it's written now, is saying that for every 2 boys, that's happening out of every 5 kids. Whereas the other one said for every 2 boys, there's 3 girls. So we're going to do the other one that goes the other direction. It says that 3 out of 7, 3/7 of the class are girls. Then what's the ratio of boys to girls? So this is kind of written like this, so I'll leave it that way. So this is 3 girls, 7 total. But of the 7 total, 3 of them are girls, which means how many are boys? 4. There's 4 boys. So I've got the 4 boys, I've got the 3 girls out of the 7 kids total. And thinking through those pieces, breaking the 7 apart, we can actually make the ratio then of boys to girls. So the boys are 4 now, and the girls are 3. So this is a 4/3 ratio, or you can do it as 4 to 3. And when we take 2 ratios and we set them equal to one another, what we actually get is something called a proportion. And one of your most common ways you've seen of solving proportions, of course, is something that's called cross multiplication. We've done that already with some of our other examples, but we will see that happening again. But if we have 2 equal ratios, that forms a proportion. This cross multiplication is theorem 620. It says that if in fact you do have a over b equal to c over d, this does form a proportion if and only if, when you cross multiply a times d, it's exactly what you get when you cross multiply c times b. So if it's a proportion, it has this equation AD equals CB. if the AD equals CB, then I can backtrack and I know that I have a proportion. Theorem 621 and 622 are very interesting because they actually create other proportions that you would knowingly have for the same reason. So if you take a look at 621, we started out with A over B equals C over D, just like on the last one. How did they get this last statement there in their sentence? What did they do to their fractions? They flipped them, like upside down, right? Yeah, they flipped the fractions upside down. That's completely fine, because if we imagined sort of setting up this ratio or something like this where we had boys on top and girls on bottom, we flipped them, it wouldn't change the fact that the statements are still true. It just changes the location. And in fact, if you weren't quite sure, you can also notice that if you cross multiply, you get the same cross multiplication pairs that we did with the other equation, right? AD equals BC. Let's do the same thing for 622. I have that same starting ratio comparison, A over B equals C over D. What happened to get the second one? What did they switch or change? Yeah, they just switched where B and C are located, right? They altered them. This is actually something that comes up when we set up proportions quite frequently. And so you'll hear me say things like, well, you could set it up like this, but you could also set it up like that. There's not often, but there's always more than one way that you could set up a proportion and makes it true. And if you take a look again at the diagonals, what do you notice? Same as before, right? I've got AD and it equals BC. Now, while it's true that I switched B and C, and that perfectly works, we also could switch the A and B, right? It's not any different. They just picked a diagonal. We could pick the other diagonal and switch them, and we would create yet another equation that's actually going to hold true. So again, a third option of a proportion setup that would be equivalent to the other two we already have. So we're going to take a look at several examples of setting up these proportions and thinking about it. So in particular, every time we look at these problems, what we want to do is we want to figure out what it is we're comparing. So it'll be kind of like the problems that you guys asked me a couple of them from your homework last time, where I put like ratio on one side and cost on the other, or ratio on one side and the number of faculty on the other. Or we did one in class was ratio on one side and we did the number of pages of the book on the other. So we want to figure out, as we look at these things, what are the comparisons that are being made and how can we work with that? And again, I'll show you a couple setups each time so that you can see that there's two different ways maybe to do that, or maybe more depending on your perspective. But let's read this one together. Jim found out that after working for 9 months, he had 6 days of vacation time. If he accrues vacation time at the same rate, right, same amount of hours every time he does his working and so forth, how many days would he earn in 2 years? So what are the things that he's comparing here? Somebody give me one. Months worth to... Okay, so we can either set it up on either side of an equal sign like this. Months worked, and these are vacay days. Or you can set it up as months worked on top over the vacay days on bottom. Okay? So I'm going to pause on showing you a second option right now, but that's the original setup. I'm just going to do it from right to left, or left to right. What other thing is being compared? It's a little bit less straightforward. Anybody see it? What do you think, Casey? The days earned is the vacation days we're talking about. So it's not that. We've already dealt with that as being one thing. There's another comparison that's taking place.
Like the months worked to the rates.
No. but you're getting closer. Kind of, but I don't think in quite the way you're describing it. The other comparison he's making is a comparison of now to later. What does he have now? What's he going to have later? That's the other comparison that's taking place. So we're going to set up a proportion, and our proportion is set up in such a way that everything on the top talks about what's happening now. Everything on the bottom talks about what's happening later. Everything on the left talks about the number of months that he's worked. Okay, we will have to take that 2 years, like Mel mentioned, and have to adjust that into months. And then how many vacay days we have. And in one of those locations, you're always going to have something you don't know. So there's an unknown here. That's the whole point. So what do we have now for the months worked? The top left-hand corner. Months worked now is 9. 9 months now. Because I've sort of labeled my columns and my sides, I'm going to leave the units off as I work. But if you want to put in 9 months, you can actually write out the word months or abbreviation. What will be his, number of months worked later? Yeah, that's the 2 years, so it'll be 24 months. Does everybody understand where the 9 and the 24 came from? Okay. So how about his vacay days now? How many vacation days does he currently have? 6. And in fact, what's missing is how many he will have later. And of course, this is assuming he's not taken them all, but at least it will tell you how many he's earned, right? Either way. Okay, does everybody see where this is setting up? Let me just show you the other setup. We're not going to solve them both because they solve exactly the same way. But if we think about it like this, where it's months vacation like this, we would have the now and the later on either side like this. And we would have the same values in the same sort of corresponding verbal descriptions, right? The now months worked is 9. The later months worked would be 24. The now vacays would be 6, and the later vacays we don't know, and that would be X. So it's an equally good setup. There's nothing wrong with it. We just need to pick one and use it. So once we've done that, we'll be able to cross multiply. So I have 9x on the top down diagonal, and from the bottom up diagonal, I have 24 times 6. So what is 24 times 6? It is 144. And then what is that divided by 9? 16. And we're working with things that have context, so our answers should have context as well. So it's 16 what? Vacation days. Yeah. Minimum, you need to use the word days because we're talking about days. Vacation is an adjective that further gives us good description, but a little bit optional. Any questions on that? So I know that maps are kind of a thing of the past. But you have maps in your phone, and you kind of do this thing where you zoom in and you zoom out, and you try to, think through what the scale is on your phone and so forth. But in a paper form map, it's a little bit more direct with an actual correspondence written on a key on there. So in our situation here, we have a city map of a rectangular park. The park has a length of 4 inches that is on the map, right? If the actual length and width of the park are 500 feet and 300 feet respectively, how wide is the park on the map? So every time we have this setup, we're going to label some pieces of information, not because I'm going to take off if you don't, but because you're probably going to put something in the wrong place if you don't. I mean, you just are. Whether it's on every single problem or just occasionally, you're going to lose track of which pieces went where. But if you label them, you're far more likely to keep them all straight. So tell me something that's being compared. There's 2 quantities. Okay, so the map length versus real life. That is definitely one comparison. I'm doing mine as the vertical. It doesn't mean that you couldn't do them as the top and bottom. There's another piece that we're comparing, or at least considering. The width and the length, and you can do them in either order. Since you said it that way, Mel, I'm going to do width on top and length on bottom. So this is almost like a grid, right? This top corner is the map width. This bottom left corner is the map length, and so on. So what does it say that we know? Well, at the top it says the city map has a rectangular park, a length of 4 inches. So the map length 4 inches would be right here. Is everybody good with that? If you want to, I'll do it this time, not because I do it every time, but just so you can see it. I'm going to leave the inches right there for the moment. It also tells you now that the actual length and width of the park are 500 and 300. So the actual length, which goes on the right-hand side, is 500, 300. And this is sort of one of those conventions of the English language. When we think about length and width, length is the one we say is longer. So when we talk about this one, the 500 would go with the length, 500 feet, and the 300 would go with the width. Now, typically speaking, they put them in that order as well. See how it says length, and then it says width? And you see the length coming and then the width coming. So they do them sort of a respectively thing like that, and they say that. So they'll do that too to try to keep it clear. And the unknown is the width on the map. Sometimes it's nice to put units in because you can see them lining up very nicely, right? These feet are lining up very nicely. My inches would be lining up very nicely like that. So that's sometimes a nice comparison piece. If I had set it up differently, it might be that feet lined up across the top and inches across the bottom. That would be another option. And we're going to cross multiply. So from the top down diagonal, that's 500x. And from the bottom up, I have 4 times 300, which is 1,200. And what will I do? Oh, we'll divide by 500. So what is 1,200 divided by 500? Yeah, and it makes sense that we would represent it in a decimal form. If we were actually measuring something, decimals is what we would use. We would use fractions or something like that, most likely. I do need units. What are my units on this problem? Yeah, it's the inches. Okay, number 5 is a bit more interesting because the setup isn't quite as direct. And yet it happens frequently like this in like real problem-solving kind of things. Kierra and Dora worked 3.5 and 4.5 hours respectively on a programming project. They were paid $176 total for the project. Because Dora has fairness as one of her strengths, she wants to make sure that each of them are paid according to the time that they spent. How much should each earn? So it wouldn't be fair in her mind to just split it equally because they didn't work the same number of hours. Are you tracking with me? Okay. So we have a couple of different ways we can set this up. One comparison that we could make is what happens to Kierra versus what happens to Dora, right? So we have Kierra and Dora. And the other comparison would be the number of hours they worked. And what else? Their pay. Agreed? Now I'm going to show you a different setup here that's uniquely different in a minute. But this one works okay, but it's a little confusing. We know the number of hours that Kierra and Dora worked, but we don't know how much money either one of them are paid, right? So both the numerator and the denominator on the left are unknown quantities specifically, whereas in all the problems before we didn't have that happen. So on the first one, the left-hand side, we can fill those in pretty quickly. Let's see, it said Kierra is the 3.5. I'm going to put it in decimal form, and then Dora's the 4.5. But we do know something about how much they're paid. We just don't know how much they're individually paid. We know the total, the 176, yeah? So what we can do, if we have it set up like this, is that we can let Kierra get paid X, and then Dora would be paid the 176 minus whatever that X is. We're going to go ahead and solve it, and then I'm going to show you a very completely different kind of setup here that makes the application, like the computation, excuse me, a little bit more direct. So if we take this one and we cross multiply, we have to be careful that the 3.5 here gets multiplied both by the 176 and by the x, right? Clear through that denominator. So 3.5 times 176, I think it's 616. What I'm looking at on my paper, yeah. And then minus the 3.5, the x. The bottom up diagonal is 4.5x. Okay, pretty good so far? Now, we haven't actually officially done a whole lot with decimals, but I have a feeling you know a fair bit about them. What would you do next? Solving for x. Yeah, we need to get the x's on the same side. If I move the 3.5x over, that will help. These add to 0, leaving me with 616 on the left. And then what's 4.5x plus 3.5x? 8x, which will nicely divide this quantity. What do I get for x? 70, what was it? 77. So to answer the first question, right, it says how much did they each make. We know Kierra made 77. How can I figure out what Dora made? Yeah, it's the 176 minus the 77, which looks like 99 for Dora. So I feel like this is the most natural way to set it up. It just ends up being a little bit more messy to solve it because we have the fraction that has a subtraction sign in the denominator. The other one is not quite as natural to set it up, and I won't do the solving for it. But one thing instead we could do, instead of comparing Kierra to Dora, is that you could compare one of the girls, and it doesn't even matter which one. I'll use Kierra since she's on top. You could compare Kierra to the total that they have, whatever their total is. So again, it would be their hours to their pay. But the number of hours that Kierra worked was 3.5. The number of hours that they in total worked was 8. We don't know Kierra's pay, but we do know that the total that they make is 176. So the multiplication's a little nicer here because there's no subtraction like we had in our last one in the denominator. It will give you the same answer. Any questions on that? All right, I have one more that's quite similar to the ones we have done, still the same kind of problem, but it's a two-step problem. It talks about a particular school. It says at Rattlesnake School, the teacher-student ratio is 1 to 30. If the school has 1,200 students, how many additional teachers must be hired to reduce the ratio to 1 to 25? Okay? So what I don't know here that I have to find first is I have to figure out how many teachers I already have. Does that make sense? So as I'm looking at what's being compared, I'm clearly comparing teachers to students. And this is much like I did in the problems from the last section and the ones you asked about this morning, or at the first part of the class today, is that we're comparing their ratio to their actual numbers. Right, so the student-teacher, or the teacher-student, ratio is 1 to 30. So that's going on the left. But the actual number of students is 1,200. So this X here is going to find me the number of current teachers. I'm not exactly asked for that directly, but I need it in order to be able to find how many new teachers need to be added into the staff. So we'll cross multiply. So we have 1 times 1,200 is 1,200, and then 30x. We divide by 30, and how many teachers do we currently have? 40. There are currently 40 teachers. Now, I'm going to do the exact same thing, teachers and students, ratio and actual, but I'm going to do it with what I want instead of what I have. So what I want is I want a 1 to 25 ratio with my 1,200 students. Number of students didn't change. I'm going to use Y, just another letter, because this number is actually how many teachers I want. The total, not the new ones, but the total that I want when I'm done. So we can cross multiply again. We have 1,200 equals 25y, and divide by 25. How many teachers do I want to have? Yeah, it's 48. So I want 48. I have 40, so how many need to be hired? Yeah. They need to hire 8. I should say 8 teachers. Let me do that. They should hire 8 teachers. Last 2 examples are things that would come from a section C kind of thing. So Mary is working with measurements and writes up the following proportion: 12 inches over 1 foot equals 5 feet over 60 inches. How would you help her? So when you're working with students, my best advice to you first is to tell them something they did right. Okay? And it makes what you're about to say that they did wrong a little bit more tolerable, right? They didn't do everything wrong. For example, on Mary's work, the left-hand side, 12 inches and 1 foot are equal values, right? So putting them in a ratio like this makes sense. And the same thing on the right, the 5 feet and the 60 inches are equal values. So telling her first that she has the sides, the individual ratios are correct. And of course, if you were actually talking to her, you would add a girler, right? Good job, you got the individual ratio set up. There is something that's not set up correctly. Do you see it? What's not set up quite correctly? Right. So on the left-hand side, I'm comparing inches on top to feet on bottom. But then on the right-hand side, I'm comparing feet on top to inches on bottom. So the ratios are in reverse order or location, or one's flipped upside down from the other one. I don't care what language you use. It doesn't really matter a whole lot. But she has them set up so that they're not comparable. I mentioned earlier on this idea that when we had, one of the things that's nice about putting in your units is that you can see the inches and the inches on top, feet and feet on top, or across the diagonal, across the equal sign, and that they line up so that you know you have them in the right locations. That's what she's missing on this. Her ratios are in reverse order. So, and again, it's another good thing to end your discussion with is to give advice on what it should look like. So it could look like, and this isn't the only choice, but let's keep our 12 inches and our 1 foot. What could we do that does make it equal? Right. the 60 inches on top and the 5 feet on bottom. And there's other ways that we could change it to make it work too, but this would be one of them. All right, one more misstepped information. Amy's friend told her the ratio of boys to girls in her classroom was 5 to 6. Amy was surprised that her class would have only 11 students. What would you tell her? Well, there's lots of things you might tell her. So if you're in a special ed classroom, you might tell her that's a perfectly reasonable number of students. There's nothing wrong with the number 11. Now, that's not really getting at the heart of this question, but it's true, right? I mean, you may just have a class that's small. We're sitting here in the class, and if everyone were here today, we only have 9 in this particular class. It's unusual, but it could happen. So one option is that maybe there really are 11. However, this is not the only way that you could end up with a ratio of 5 to 6, which is really more of what this question is trying to lead you. So think more of a traditional classroom setting. Maybe you're teaching 2nd grade or something like that. Probably don't have 11 kids. It's probably more than that. So you might talk about the fact that this ratio of 5 to 6, and I'm going to write it in fraction form, is equal to 10 to 12 as well. Right? That's the same ratio. If you multiply the top and the bottom by 2, you get 10 to 12. This would yield, if you're thinking about it from this perspective, 22 students. That might be quite reasonable, right? Elementary school classes, 22 students is a fairly typical kind of number. But it's also possible that if you multiplied by 3, you'd get 15 over 18. So it'd be quite a lot, 33 students. But that'll sometimes happen when you're working in a middle school, right? The ratios don't necessarily hold all day long. You might have a class of 12 and you might have a class of 35, right? As long as there's another desk in the room, you can fit them all in there, then they think that's okay, right? That can happen. So it might also be that you have 33 students. So do you notice a pattern? You might have 11 students, and you might have 22 students, or you might have 33 students. What's going on? How are those numbers related? It's going up by 11, or you can say that they're multiples of 11, right? So the ratio being a 5 to 6 ratio means we have 11, 22, 33. We could continue going, but heaven forbid you ever have 44 in your class or 55, etc. And it would actually still hold, right? It would. The ratio would stay the same if you had any of those quantities of students, the 5 to 6 ratio. So the 5 to 6 is simply being used most likely because it's the reduced ratio, not necessarily the actual number of kids ratio.